Alright, how y'all doing? I'm Texada, and I'm here to tell y'all about I'm group reporter for the engine performance experiment. Basically, we're in there running an internal combustion engine. Alright, obviously, as I said, we're running an internal combustion engine. We've gone over these like 5 times now, so I'm assuming y'all all know what they are. Alright. Just a quick view in case you forgot. This is a 4-stroke per cycle engine, so there's a intake, compression, where the gas is compressed, spark plug ignites it, produces power, and then it's all spit out in the exhaust station. So that's just a quick review of what it goes over. So this is the experimental setup. Well, we have a engine kind of right there. That's our engine for the experiment. It's a 13 horsepower OHV single cylinder Predator engine. Basically just kind of a small engine you can buy at a hardware store. We connected that to it's been connected to a dynamometer, which is basically a device that allows the water to act as a measurable load on the system, a pretty well-defined load on the system. So that's the engine, that's the dynamometer. The engine is controlled through a series of actuators that control the fuel flow and throttle in the engine. And that's a detail on the dynamometer because it's got a really cool name. Right, click it. So diving headfirst into the equations, our first set of experiments runs we did were running a constant load and varying the RPM on the engine. So this was at 0% load. This is the horsepower versus RPM. You can see the horsepower and RPM go up steadily, and then eventually the horsepower will start going down. This is when the horsepower overcomes torque, and it's just kind of peak. I don't know what that giant peak is at the end of the line at the graph. I can't really explain that. So this is the torque versus RPM versus for the same thing. It kind of mirrors the horsepower. You can see it goes up and then it'll drop. This is for 10%. If you didn't notice the numbers on the previous one, the horsepower is higher on this run because it's got to support a load now. The line's a little bit different. The peak isn't until at the very end, and I'm not sure if that's actually a full peak or not, but it did start to go down at the end, so I'm going to call that the peak. The torque here doesn't mirror the horsepower exactly. There's a kind of a weird lump. I'm not really sure what that's about, but that's just data recorded. The peak's a little bit easier to see on the torque, but it's still kind of minor compared to 0% load. Alright, so this is where we had a bit of an issue with saving the data, I'm pretty sure. Where those previous tests where we only managed to record like 1 second intervals, somehow that got turned into every thousandth of a second was taking a measurement, which is why there are so many more data measurements here, but I went ahead and plotted them all because I don't know how to use Excel to reduce the number of intervals. Anyway, it's the same thing. There's a weird lump right there. I believe that's the peak of the system. The data was kind of weird, so go ahead and click. But the torque, I think, shows the peak a little bit better. But again, there's all that end is kind of weird. I really don't know what's going on with some of this because our data was kind of weird. All right, this is the 30% load. They gave the highest load. Notice the horsepower is roughly 4 times as high as the 10% load, which makes sense. I mean, it's not quite a linear relationship, but it's pretty close. We have a pretty clearly defined peak here in the horsepower. And then we also have a weird circle. I don't know what causes the circle. It showed up on the data. All right, this is the torque. Again, the peak is really well defined on this one, but we still have a circle. Don't ask me what the circle is. All right, so then the next battery of tests we did were running the engine at a constant speed and upping the load on the engine. This was done every 10 seconds, or roughly 10 seconds, we up the load. And the horsepower graph clearly shows this. We have a very sharp jump, very sharp jump, very sharp jump, and an incredibly sharp jump. Each of these jumps is where the load was increased on the engine and this whole time the RPM but it's kind of, even though it says constant RPM, the RPM does go down a little bit, but that's just because we're running the engine at high loads. This is the torque. It kind of mirrors the horsepower pretty well. Not really much else to say. This is the second run. It's pretty much the same thing. Click. This is the torque for the second run. Pretty much the same thing. Click. Again, here we had the issue of the data getting kind of wonky and having way too many things. This is horsepower versus time for the third one. But this one shows it's pretty much the same thing then. So click. And that's the torque for the third run. Pretty much the same thing again. Click. All right, so what do we do with all this number all that data we just showed you in a bunch of graphs? We can calculate the air mass flow rate, the volumetric efficiency, the conversion efficiency, aka the fuel efficiency, and the mechanical efficiency of the engine. Click. We can also find the brake mean effective pressure and the power of the engine. I mean, I realize we reported the power, but we can calculate the theoretical power of the engine too. All right, click. So this is the fuel and air flow rates plotted against each other versus time. This is all done on the constant load, the constant RPM run. The air flow rate's a lot higher because the fuel to air ratio, or the air to fuel ratio is high. So here's where we run into a bit of even more issues with the data. The data, following those equations perfectly, I ran them like 3 times using equations I got from the book and everything. Our volumetric efficiency is pretty close to where it should be, around 96, 97%. And then there's the issue of our conversion efficiency. It's supposed to be around like 40% maximum. It reaches like 103% here, which is nowhere near reasonable. I don't really have an explanation of why the data is that. It should roughly be a third of that. And because of the fuel efficiency so high, the mechanical efficiency is actually really low. It only gets to around 30%. Mechanical efficiency should be a lot higher than that. All right, click. The BNET, the only thing to notice about this graph is that you can basically see where the load was increased pretty accurately, right there and right there. The other thing to notice is kind of like where it goes up and then it kind of goes down. It goes up and then kind of goes down a little bit when the load is increased. In the power comparison, this is calculating the theoretical power versus the power we reported. Again, because our conversion efficiency was off so much, the theoretical power is way off, but it does show kind of the same pattern. If you took a more reasonable conversion efficiency, the theoretical power matches the actual power a lot more closely. All right, so those are my references. And do you have any questions? Any questions?